live and on location. This is Mr. Hudspeth's neighborhood. So today we're going to be going over ball to roller bearing conversions. And Jim Hudspeth will be going over a PowerPoint with you. Also, just a reminder on your pump training to finish that. I don't think anybody's done it yet. Nobody's got any money or a certificate, so you might want to finish that and be the first one to do it. So now we'll go to Jim.
Hi everybody, Jim Hudspeth. So listen, today I wanted to get into a handful of things about roller bearings and ball bearing conversions, so I may be jumping around a little bit. LA, I printed out these for Reno. It's basically the bearing chart showing the cylindrical and ball bearing tolerances for the shaft journals. So you, Richard, are going to have to probably get them that after we're done, I assume, just so they got a better idea what's going on. Okay, Dan, let's go ahead and flip. This is a Baldor 200 horsepower Reliance Baldor, and basically it was a ball bearing that was converted to a roller bearing, but we're going to go both ways during this class just so you get a better idea of what's happening, okay? It doesn't matter really which end you lock when you're locking the roller bearing or the ball bearing. It's preferred to be the drive end. Now I've seen a lot of motors, and most of the time the opposite drive end seems to be, but the reason for this is whatever bearing you clamp, when you clamp it, it's going to expand away from the clamp. So if we're clamping the opposite drive end, we're going to be allowing the shaft to grow towards the coupling. So you could see a problem if we have couplings that are laser aligned and facing without a gap in them, where our shaft could grow and maybe make contact with the other coupling and try to bow, okay? Or preload your bearings at that point for growing too long, all right? Like I said, the clamping can be done on either end. It's preferred to be on the drive end, so it's not to influence the coupling during the alignment or the driven component from axial thermal growth. A lot of you may not know how much thermal growth is, but we're going to get to that in this, just so you got a better idea of what can really happen, okay? When we say clamping, we're talking about securing the outer and inner races, meaning that we want the bearing cap or caps, depending on if you have two caps on one end belt, to squeeze the outer race of the bearing where we're clamping it. So we're squeezing the bearing with the two bearing caps. The bearing can't rotate, can't move. It's tight, being held, okay? We need to install a lock nut or a snap ring to secure the inner race on the same end where we're trying to clamp. And at this point, both inner race and outer races are not able to move axial. So that's holding the rotor from being able to move by squeezing the outer and inner races on the shaft, okay? This is the clamped end now. So depending on whatever end you're going to do, that's going to be the end that is clamped. So if it's the drive end, it's going to grow towards the opposite. If it's the opposite end, it's going to go towards the coupling as far as thermal growth. This is the same Baldor motor. So you can see over here, this one has the threads for the lock nut. You have your register up here on the cap, and then your bearing goes on to the shaft here. When we do this, guys, just remember, when we go from a ball bearing motor with ball bearings on both ends, and we go to the roller bearing on it, it's not a big problem. We have plenty of room in the roller bearing to absorb any small amount of misalignment, okay? When we go to a ball bearing and a ball bearing, that's a problem because now we have very little tolerance in the actual bearing itself, so we don't have very much room to work with. So if we're just 5 thousandths off, we're going to be preloading one end or the other end. And it's real easy to do. So it's real critical to get these dimensions correct when we're doing the ball bearing from a roller bearing, okay? But anyway, this picture here is showing where we're locking the nut and the lock washer with the bearing cap. Same thing right here. It's the same end as far as that goes. That is the roller bearing conversion on this one.
That's a good question.
Yep.
With that washer and that nut, instead of having an NU bearing, can I switch it to an end bearing? That way the rollers are on the race and then the OD
You can.
in the housing. That way way it's a little safer with that.
Well, you can, because it's easier to install it without having to use all threads in these two holes and draw it in. That's a pain because you don't, if you have a blind end bell going across to this thing like that, that is hard to put on. You actually have to have the rotor pulled out of the stator, put the end bell on with the all threads where you can see the cap, squeeze it all together, and then push it back in. It's a pain in the ass. So if we went to an end style, it would work fine.
They do share the same load then?
Yep, the same load rating and everything. So there's not a problem there. And yes, we've done that here. We've switched to ends to make it easier to assemble the assembly process. You can't get that, you can't put the bearing on after the lock nut's on. You can with the end style. You can put the whole roller cage with this all on and just slide the outer end portion back in to the housing. Okay, so eventually here we're going to get into the tolerances. That's what I was talking about. The Baldor Reliance only uses one bearing cap on this motor. So it's an inboard bearing cap that's in the photos that you're looking at. So the bearing must be bottomed out in the housing. So the end that we're clamping, we have to have the bearing in the bottom of the housing. We have to have the cap with the register touching the outer race. So we're clamping the bearing, okay? The outer bearing cap will squeeze the bearing till it reaches the bottom of the drive end of the housing. So it depends on, like I say, whether you're opposite drive end or drive end, doesn't matter. Just make sure that we're clamping the bearing so it's in the housing tight with the caps, as well as the nut or snap ring on the shaft. If it doesn't have a snap ring or a nut, put a snap ring groove in and put a snap ring on it. That's the safest way to do it, and it works relatively easy. Works good too, okay? Measurements must be taken to make sure that the cap compresses the bearing into the bottom of the housing. So you want to take measurements in the housing, get the total depth of the housing, get the registered depth, get the width of the bearing, and calculate what it's going to take to get those two to squeeze. In a lot of the cases, we're able to cut the bearing cap deeper. So in other words, we're not cutting the face that touches the outer race. We're going to cut the part that goes up against the surface and make it go in further. So the bearing cap in the photos, when we're looking at them, just remember that all we, Dan, go back one slide. That's good. We would be able to cut right here and make this register extend further in if we have the meat. So when your bearing is up here, and say you have a 100 thousandths, you could cut this back 100 thousandths and extend that in to make contact with it. So it's a relatively easy thing to do in most cases. This particular motor, we had to make a spacer, Ramon had to make a spacer that was almost a ½ inch thick to go into the housing so that the bearing would go in up against the spacer and then the cap tighten up, okay? There's times when we haven't been able to do that, and then we have to make a spacer and put it in right in front of this register on the cap so it would squeeze it, okay? Okay. Again. Okay, next one. Okay, when you're doing this, we don't want to change, by doing any machine work, any of the paths that allowed the bearing to get the grease. So when you're looking at it, make sure that if you build a spacer, you don't build it so that it blocks the bearing. You know, all we want is a thin spacer that's going to go around the outer race to squeeze. We don't want to block any grease to get into the bearing because we covered it up with part of our spacer we built. So you could make a spacer a ½ inch thick going down and block some of the grease to get to the bearing, is what I'm trying to say. All right? So make sure that you don't block any of the paths for greasing so that everything stays the same. All we're doing is securing the bearing so that it can't move. And dictate exactly where the thermal growth is, okay? 6319 drive-in, 6314 opposite drive-in. But this is what I'm talking about. Generally, you're going to put this together, and on the opposite drive-in, you would normally have the shaft growing, which is what this one's doing. The drive-in has the nut on it, so we're going to grow that way. So we're going to want to make sure that we have enough room in this housing at the bottom so that that bearing can go in the housing and move that way without being preloaded from thermal growth. This is the opposite drive-in of the same motor. So you can see that the bearing's been installed on it. It has a snap ring groove cut in it now. It didn't before. All right. So snap ring will go right here. This end of the motor, we want the bearing to be able to move in the housing. The bearing housing cannot be tight. So when I say move in it, I'm talking about basically sliding. The term loose, let's say it this way, the bearing can turn but not rock. That's a good phrase to remember. So if it turns, it's not a bad fit. If it moves by itself in the housing and it rocks like this, that's a bad fit. We want it to be able to grow with the shaft having the bearing on it and actually have the whole bearing going in the housing towards the opposite drive-in this case, so that it doesn't preload. If we lock both ends of our motor, we're going to have our shaft trying to grow with no place to go. It's going to take out both bearings, depending on which one's the weakest, so the smaller bearing would be a problem quicker. And we don't want our shafts to try to bow. Okay. The term spin but not rock, so just remember that's a good one. The bearing cap should have the register cut 20 thousandths off of the face where it touches the outer race. This stops compression on the bearing outer race. So in other words, when we put our cap on this one for the opposite end, we don't want that register to try to pull the bearing off the journal. We don't want it to move on the shaft. Okay, so when we put the bolts into the housing and we start tightening it up, if that cap was to touch the outer race on the opposite end, we'd be trying to actually pull the bearing off of the shaft or preload the hell out of the bearing. So by taking 20 thousandths off of this cap, and that's just a recommended number by ESA, which makes sense. Any clearance is clearance. But you just don't want it to have growth from things swelling up with heat. All right? So we're going to take 20 thousandths off of that cap so that it's not being compressed on the ON. The whole shaft with that whole bearing is going to try to grow with any thermal towards the ass end of the housing. Okay? Housing needs to have some clearance so the bearing can grow axial length for the shaft. So just out of kicks, if we had the same motor again, this is a 314, you can see right there, 6314, how much room should we give it for the shaft to be able to grow without internal preload? How much do you guys think that we would have to have in the housing room to grow?
How long is the rotor?
So it's a 200 horsepower. Between me and you, between bearings, we're probably 30 inches, something like that.
So 30 thousandths at least, 35.
From 80, 100,000.
Okay, okay, all right. Let's go to the next slide, Dan. Okay, so this is the one where I want you guys to basically start really paying attention to it, okay? Calculating the axial shaft thermal length growth. Now we calculate the shaft thermal growth for the axial length of the shaft between bearings. So we're going to measure between our two bearings. All right. So at this point, what I'm trying to say is that if we have a shaft that's 5 foot, that big Tico that we just shipped out, that motor would have been very easily 60 inches between the two bearings. The rotor was from Dan to me long. So that's the number, because we're looking at how much the shaft can grow between our two bearings. Okay, so our bearings are what are being held, and we want to make sure that we see how much room we're going to grow and calculate it. All right. So real quick here, these are inches of the length of the shaft between bearings. This is calculations for 40 degrees Fahrenheit. This is the distance that it moved in thermal growth at 40 degrees. Okay? So a 60 inch, which would be 5 feet between the two bearings. It's a very common size for you guys in LA. You guys do a lot of 2,000 and 3,000, 4,000 horsepower stuff, and that's about the right length for one of those type of machines. All right? So if it was 40 degrees and you were that distance, you'd move 16 thousandths in thermal growth. Dan, go to the next slide. A little more. There we go. Okay. So using the formula, 60 inch between bearings, and now our shaft being 150 degrees. You guys take motors all day and do bearing tests and runs. How hot do your bearings get? Average.
100.
Anywhere from 100 to 150. Real easy. I mean, average two poles, 135 to 160 on a rough idea. So this is not real, or not too hard to get to is what I'm trying to say. Temperature-wise, 150 is not all that bad. 180 degrees Fahrenheit all the time. But by doing the equation with that one, we're 60 thousandths. And that's at 150 degrees instead of 40. It was 16 thousandths when it was 40 degrees. So as a machinist, you guys especially should be able to calculate this and come up with a number, and then I want you to add another 20 thousandths to make sure. Because here's the scenario. Today, you've got the motor over here on the test pad, and we're going to run it, and it's nice and cool in the shop, 60 degrees, whatever. You run it, your bearings stabilize, you have no problems. You were back at 16 thousandths if we had that last page up again. Now the motor goes to the customer and it sits out and doesn't go into the job until next summer for some reason. Now it's 110 degrees outside. You start doing the calculation again, and all of a sudden you're back up here from 16. So your motor ran fine here in the shop and you did everything right. Your bearings stabilized, you ran it for an hour, whatever it took to get there. Everything's good, vibration's all good, but yet the customer goes and gets it, and 2 days later he's got bearings that look like they were beat the hell out of like certain cement plants. So to give you a good idea, you are not calculating the thermal growth in the housings deep enough, and the motor was running fine because it wasn't preloaded on the opposite drive end because there was clearance. As soon as we took it up to the higher temperature of the rotor and allowed it to expand greater, we preloaded our two bearings, and it doesn't take very long at all to take it out. I mean, we're talking about days or hours in comparison to a 10-year lifespan for a bearing job. So it's really critical for you to make sure that when we're taking the dimensions, we use this formula and say, okay, we're going to have an estimated 60 thousandths that we have to deal with. I'm going to make the housing 80 deep. We don't want it to go a half inch deep or whatever more. We just want to make sure that our shaft can grow and go from there. Okay? And then you should be good. So to give you a better idea, these shafts grow a lot more than you would think. We took a 22-inch piece of material. We ground off both ends of it so that we could measure accurately from end to end. Ramon, myself, and Marvin, we put it in the oven. We brought it out and measured our temperature at 135 degrees. We had 21 thousandths growth, and it was just a piece of 2-inch diameter pump shafting. So 22 thousandths of preload, oh my God. It wouldn't take very long at all to have something seriously bad happen. And I'm convinced that we've had motors in the field do this. I've many times said, look, it ran fine here, it's got to be your problem, when it really could be ours. We sent out with not enough room to expand. So we want to make sure that we take these calculations and do them correct. allow for the growth to go the right direction. The idea of clamping the drive end is something I've not done that much of. It's always been the other end, but I didn't know what I know today. So what I'm trying to say is that we want to make sure that we can clamp the drive in if we have the ability to. If we're putting a roller bearing and going the other direction, you can't clamp it. If you're using an NU roller bearing, you can't clamp the drive in. It has to, well, you're going to clamp the outer ring, but you're going to allow the shaft to grow through the NU part of the bearing. So it can grow, it will grow to the drive end. There's nothing else you could do with it. So you're going to have both situations, is what I'm trying to say. But the whole idea here is to make sure that we do this. You two machinists have to, you know, I'll work with you, Marvin can work with you. Mechanics, you need to know when you see one coming in that has cratered bearings on both ends or one of them really bad and all that, that we better start looking at the clamping real good to see if there was something caused that we clamped it wrong. The last people who had the motor, I don't necessarily mean Reed. Yes?
We had what just come in.
You did? Which?
10, 21, 22, I think. We had an NU bearing and the inner race started walking off the shaft. I got pictures on it. It wasn't clamped.
Okay, so let's get to that now that you brought that up. Okay, so Eli said that the inner race started to walk on the shaft. Okay, so number one, we're working with heat again and things expand. The inner race is only maybe on average 1/4 inch thick, so it doesn't take a lot of heat to expand a 1/4 inch type material like a piece of pipe, because it'll just grow. If you guys look at the bearing chart that I've got, I highlighted 100 millimeter bearing just because it's a round number and everybody would see it. I want you to realize that we're looking in the purple at the ball bearing fit. So the maximum diameter of the journal for a ball bearing is 3.9377. That's the maximum for a ball bearing. Change to the next page. This is the roller bearing fit. They are not the same. A roller bearing is almost double what a ball bearing is in radio capacity. So if you got a ball bearing good for 10,000 pounds of radio thrust, you have 20,000 with a roller bearing, capable. So what I'm getting to here is it's double. So you have to have that shaft tighter to hold the bearing because you got twice the load as the ball bearing was that you took off. So if we look at the same one now you're looking at the minimum the roller bearing can be is 39379. So can anybody tell me, just looking at those two numbers, if they see something here?
It's 2/10 off.
So Cody says it's 2/10 off. What? Give me a better answer.
The maximum, the minimum is still 2/10 off.
It's 2/10 under, is the word I'm looking for. So the roller bearings going on to a fit, that's already 2/10 of a thousandths under size. That's why I'm having you guys always Loctite the inner race of the roller bearings. But there's two things. One, always use the bearing if you have it here that you're going to put on the motor for the measurements. So when these guys are in the machine shop and we're going to use a 29-434 or we're going to do a 29-438, I want you to use that bearing for your measurements. It's a new bearing. It's the one you're going to put on the motor. Measure the outside and the bores so you know what the actual sizes are if you're going to put a sleeve in it. So if you're going to bore a housing or sleeve a housing, use that bearing. Bearings come under or over. They can come a thou easy, over or under, real easy. I would have never believed it in my younger days, but believe me, I've seen it many times. So not only that, you're playing again with thermal expansion. You guys measure the bearing when it's 45 degrees in Reno. Let's just say it's a fluke day in LA and it's 80 degrees. I'm not going to get the same readings on the same bearing. I just showed you thermal expansion, what the formula is. So you could sit there and actually calculate how much that bearing is going to expand or not expand just by having the room temperature different even. So the key here is that you need to measure your journals. I know Tim sells a lot of motors and we convert them. I know you guys need to go back and measure the journals and make sure that for the roller bearing conversion from a ball to a roller, that you've looked at that damn chart and made sure where we're at. In some cases, if it's too low, Loctite ain't going to work. You're going to have to use then a metal spray or a Belzona product or something.
Yeah, sometimes the journal is not coming in the maximum size, coming between the maximum and me.
Yep. And that's normal for roller bearing and ball bearing. So now the problem is looking at the ball bearing maximum and the roller bearing minimum and seeing if you're going to be able to use it.
We can machine a persona machine the maximum size for rolling.
Well, then you can put it back to what the chart says. Measure your bearing that you're going to use. Because what if the bearing bore's a little smaller? You put the max and your bearing's a little smaller, you're going to run hot. So you two really are important to make sure that we get the right tolerances for the roller bearing conversions and stuff. And nobody wants to take a brand new motor and do machine work to it, but if it has to be done to keep the bearing from failing or walking off the shaft, because it was too small a diameter when we put it on, and that's probably what happened in this case. So when I say this, I know you guys are tearing motors apart that we didn't work on, but I just want to make sure you realize that when we're doing this, look at the journal, measure the journal, make sure where it's at on the chart, and advise the machinist of what you see. They're going to go do it themselves too. They're going to always check your work anyway. But that's good. Two sets of eyes will catch things, you know, and make sure. Okay. So again, I want to make sure that when we talk about ball bearing to roller bearing and so on here, roller bearing conversion is the easiest. Having the NU, the shaft can grow with that inner race, not touching anything, 60/16th of an inch. So as far as a roller bearing goes, most of the time on both sides of the roller, if you were to measure it to the crowns on the inner race, you're going to see that you've got probably a solid 1/8 of an inch easy on both sides most of the time, or somewhere in that area, depending on how big the bearing is. You know, some of the races are that big, some are that big. But my own opinion is that knowing what we're talking about today, hopefully you'll look at it differently and say, look, something's internally causing this problem from preloading. My journals are undersized. I need them bigger for the roller bearing. I want to make sure that I Loctite any inner race for the roller bearing. We don't want it to walk off. If you put a snap ring in front of the NU type bearing, that's fine. There's no problem doing that. That helps keep that race from walking off. Do you remember the 300 motors we did for our power company? Okay. Those motors had those inner races dropping on the shaft and destroying the motor until we put snap rings and all that stuff in them. Same thing. Okay.
Question for you, John.
Yes.
So for the thermal growth, some of the motors that we tear apart that come in with the roller bearing in them, where the inner race is inside, or the rollers look like they're overhanging the crown just a little bit.
Thermal growth?
Is that designed that way for the thermal growth, where that would put the inner race right into the rollers? Or is it like a 50-50?
Yeah. I don't know the answer to that. I'm going to say my own opinion is no. Because I haven't figured out yet what temperature I would say every shaft should be.
Yeah.
So I can't give you 125 degrees, 150 degrees, or 100 degrees as a number. That's why the equation was set up so you could plug in the temperature that you know it's going to be.
So a safe bet is just always make sure that your opposite side for roller bearing is clamped, and then either machine the bearing cap or put a spacer in to make sure that the rollers are center of the sleeve.
Yes, because I think if it's at the end of the roller race, it's already wrong. Should be in the middle, even if it wasn't calculated for any growth. And in this case, the housing is going to stay stationary with the shaft trying to grow. And if we had 60 thousandths as a number, I would say that you'd be still within the crowns of the two motors. Okay? As far as that goes. The chart, I can't say this enough. I keep telling every mechanic that I see and work with all the time, Roller bearing is not the same. You see on your chart, it has a tolerance here, and if you look up the tolerances for the ball bearing, it's a K5, and if you look at the roller bearing, N6. Okay, those are total different tolerances compared to ball to ball. You're not working with the same. So it's very critical to make sure that our machinists get the journals within the tolerance they need to be for the roller bearing. If you're pulling a bearing off of Belzona, you're most likely going to re-Belzona the shaft. Most of the time, pulling the bearing without any heat is going to cause the bearing to be undersized on the race, the shaft bit. If you use any heat on Belzona, you're doing it over already, because any heat on Belzona is going to bubble, it's going to flake, it becomes a problem for the Belzona to adhere to the shaft. So, I mean, you know, when it comes down to any guesswork, always go with the repair so that it's done right and we don't have any warranty issues and everything's good. Okay, as far as that goes. Let's go to the next one there. So once again, I want you to just kind of think about this for a moment. What happens if there's not enough clearance on the non-clamped end? So we're clamping the drive in this case, and the opposite drive in. Let's say we have 45 thousandths clearance in the non-clamped end of the bracket. That's a lot of clearance. All right. And it was 75 degrees. We test run the motor, and the bearings both stabilize, and we're done and ready to paint. Next slide. Do the math again. 60 inches times 125 degrees Fahrenheit. This number is wrong, I apologize. It's supposed to be the formula number 0.000067. Comes out to 50 thousandths. So what I'm trying to say here is that both bearings are now preloaded by 5 thousandths by bearings. So again, doing the formula, this number right here should be point with 5 zeros and 6 7. I didn't catch that until now. So it doesn't, you know, again, in your shop, everything's running fine. You don't see a problem. You don't see vibration issues. But as soon as we get it running hotter in the field, or at a different time of year, let's say, now we grow longer and we bottom out into the bottom of the housing and everything goes to hell. Okay, let's see what else we got. Shaft bits, roller bearings, shaft journal versus ball bearing shaft sizes. When we change the ball bearing to a roller bearing, we need to measure the shaft journal for size and compare it to the roller dimension. I would always use the roller bearing again. If you have the bearing here, use it. If you don't, go by your numbers. That's the best I can tell you. If it's a big bearing, I want you to force somebody here to get the bearing to you. I don't want to have you guys do machine work on a shaft that's a 29-438, not have the bearing here. You need to have the one you're going to use so that we don't do the housing wrong. We don't need a 1,500 horsepower motor having hot bearings or wondering what the hell's going on with it. The machine work done right when they have the size, they hold the tolerances that we have in the specs, but they use the physical size of the bearing to get there. And it's a lot better way of doing it to make sure that you're not a thou under or a thou over, which can both be kind of detrimental to it. All right, Loctite 609, which is the permanent Loctite. I don't care if you're using Permatex or Loctite or whose brand, but we use the 609 here in Reno. So you should use that on the shaft bit for the roller bearing on the inner race. Make sure that's done always. Otherwise, you could have this small fit all of a sudden becoming a problem. The inner race walking off, just like you described, Eloy. Same thing.
Can I add something to that?
Yep.
When you're using a Loctite, just don't put the sleeve on and then walk away. It'll puddle and then caulk that race because of when you heat that up, it slides on. The Loctite will puddle, and when it dries, it will caulk that race. Put it on, keep spinning it up against the shoulder until it stops. That way you have an even pattern with the Loctite when it dries. When it puddled on us, that inner race cocked and it kept messing up the vibration on the test pad, and that's what we found out was the Loctite was puddling underneath the race.
Okay, next one. Both ball bearing and roller bearing charts are attached so you can see the differences in the journal sizes. LA didn't have those charts, so we'll go to the next slide there. So what we're looking at, ball bearing fits for this tolerance sheet. I picked 100 just because it's easy to grab and everybody sees a 100 millimeter bearing. All right. So the maximum size for the ball bearing fit is right there, 3.9377. Next one. Now we're back to the cylindrical roller bearing on 100, and you can see now the minimum that roller bearing fit on the shaft can be is 9379. We're 0.2 of a thou under already before we even started. So that's why it's so critical to measure the shaft that we have, measure the bearing that we have, and you could still be okay. If the bearing came in a little smaller out of the box, and this fit was on the shaft journal a hair of, 0.2 larger or something, we'd be in good shape. We'd have no problem. But we need to calculate that and make sure. That's all I'm trying to say. You just can't, it's within tolerance. So looking at roller bearing versus ball bearing in the machine shop, we want to really look at those numbers, okay? We don't want to have a problem. This is where you'll start seeing journals becoming grooves a 1/4 inch deep and all that stuff from spinning and having a problem.
Is there a size of a roller bearing where we can get away with using Belzona before we have to metal spray it? Or should Belzona cover all sizes of roller bearing?
Oh, as far as enormous versus small?
Metal spraying the journal versus using the Belzona for the journal.
I don't know that one. I don't know, in other words, if I had a roller bearing that had a bore this big, what I would want to do yet. I'm serious. Sometimes that would be chroming. When you get into enormous shaft sizes that have that much side load, we'd want to be careful whether we'd want to use an insulating product like Belzona.
Yeah.
Okay. I mean, we've had no problems with it in some very large equipment, but not something that big.
Yeah.
You know what I mean? 10-inch shaft diameters is a different story. I'd want to make sure we really looked that close as far as coatings go. I think that concludes pretty much. Is there any more left on it? That's what I thought. So I hope this is something that's brought some eye-opening here, just to make sure that learn the formula and make sure that we start calculating how much we're going to machine. In the old days, all I said is, Ramon, take 20 thousandths off the housing. I didn't know. I know now that we should be calculating the number and give it a little more. A little more is not going to hurt anything. So we'll give it an extra 20. So if it was 60 thou we calculated, we'll go 80 for clearance on the opposite clamped end. Okay, just to make sure. Any questions from you guys? Yes?
Compression and preloading the same thing?
Compression will cause the preload. So not the same thing, meaning that we have the cap on the rotor and we have our bearing sitting here, okay? So there's a gap. And as we pull the bearing up, if it's not lined up on the outer race with it, we're going to try to pull the shaft in with the outer part staying in the same location. So we're taking that bearing and pushing it like that. That's preloading. So pushing against the roller or the ball, axial, would be preloading it. The cap would be the problem with doing it. So by tightening up the bolts in the cap and drawing it forward, it has two choices: either move on the journal and go with the cap, or stay on the journal and force the balls to move out of the center of their raceway. So, a regular bearing is got like a U, and the ball is in the middle, and you could have maybe 2, tops 3 thou movement, trying to push that ball off of the center of the pathway. That would be preloading. You'll catch it most of the time in the test run, but you could destroy the bearing real quick. How long did it take when we preloaded a vertical motor with the bearing in the bottom? 6228.
10 seconds.
Yeah, 30 seconds tops. We preloaded the vertical with too much end play. Okay, we took out the end play, fired it up, in 30 seconds we smoked out the bearing. Took it apart and had a nice big groove in it, pushed off to the side. You could see it real dramatic. So it only takes just a few seconds. So I could see us having a shaft and a motor running in the shop just fine. Next time it goes out, it gets hot, and they install the motor out in the field. First day or so, no problem. Then all of a sudden, here comes the motor back with the whole front end of the motor cooked out of it or something stupid because thermal growth. Learn the calculation for thermal growth. It's a big one. The rule of thumb, and this works relatively easy, and Marvin and I have talked about it, so that's why he knows it as well. 10 thousandths per foot. This is for cold roll standard steel. For stainless, it's 15 thou per foot. So if I have a 3-foot shaft, 30 thou. Quick numbers. So remember that. If you're, I don't care what you're building. This could be have nothing to do with a roller bearing. It could be 2 ball bearings you're doing, and you're putting something together that's a gearbox, whatever. Just start thinking in your own mind that if I got 3 foot of distance between my 2 bearings, I could have 30 thousandths of growth.
Or 45.
Or 50, yeah, depending on the temperature that we plug into the formula. So it's a big thing to remember and to know. It's like having couplings and stuff. You know, another problem we're going to get into down the road here is some couplings and pillow block bearings. Pillow block bearings, I'm starting to see, are a lot more than just buying 2 little pillow blocks and sticking them on and saying we're all done. We'll get into that because there's enough details to go on pillow block bearings. It's a concern to have its own little class for too. Okay. Normally speaking, you're not going to have 2 of the same pillow blocks being used. I had you put the ones on the oven last night. So our oven had the motor in the back that drives the fan that puts all the air into the box. The bearings died. So Eloy replaced the bearings last night and reinstalled it back in the unit. Both those pillow blocks were of the same type and both clamped onto the shaft. Do you think that fan gets hot? Why? It's in the oven. So it's pretty safe to say that it could get up to 200 degrees. So if we started plugging numbers in, our little shaft, which is about the same length as the one that you and me measured, is going to grow probably 20 thousandths and preload the hell out of the 2 bearings we installed. So they have bearings out that are called non-expansion and expansion type. Okay, so expansion type allows the bearing to move in the pillow block for the thermal growth. So make sure that we know when we're doing this which end it's clamped, where we're growing to, and how much room we've got to grow. Or we're going to have problems in the field doing alignments, doing installs, and all this other stuff. And I know that when we've been getting pillow blocks, we're ordering what we got from the customer by number. Well, some of these bearings come a little bit universal, so they can have a sleeve piece come out of it that allows it to grow. Leaving it in, don't let it grow. So you could have bought the right bearings, but didn't know which one went to which end, or didn't know which pieces went on which side, and create more headaches down the road for a job you're doing in the field that might be 400 or 500 horsepower with a fan sitting over here running hot air, you know, or hot product, whatever it is. So I'm going to get into the pillow block bearings more, but I need to do some more homework on that one first before we get there. That's all. But I don't expect our bearings to last forever, and when they do, it's only because we're running the oven for a shift and turning it off. And it might not run for another day or 2. 24/7, we probably replace them in a week. So we're probably going to be changing those out again here with the right bearings is what I'm hoping, okay? So make sure of that. So just remember that when we're out in the field. There's some more stuff here that we got to go over to make sure, all right? Okay, that's all I've got. Anybody else, anything?
For the clamp in on the opposite drive-in side, can I use a wavy washer, or should I replace it with like a solid ring?
For clamping it?
Yeah.
I wouldn't use a wavy washer for clamping it. I would, because you're going to get hard measurements trying to get the bows and stuff. I would go with a regular spacer and clamp it hard. You know, don't put any more than about 10 thousandths behind the cap in the housing. So where the cap is here and the housing comes up and it's squeezed, you want about a 10 thousandths gap to make sure it's compressing and squeezing. But you don't want to break the cap by trying to pull the bolts in and have it snap because you got too much of a gap between the housing and the cap. You know, a 3/8 bolt and the little impacts you guys got, snap that cap right in the back. It's just cast iron most of the time, or aluminum in some cases, or whatever. So I would be careful with that as far as that part goes. Okay. Anything for? Oh, go ahead.
Is there a certain speed range for roller bearings?
Yeah,
So
absolutely.
So for a certain customer we do work with, if they're over speeding their motor and they have a roller bearing on there, could that be some of the cause of failures for their?
Sure, it could. Yeah, absolutely. So anytime you're looking at that, we can look in the bearing books for the size and the brand and get relatively close. What you have to be careful with is if we're looking at a roller bearing per speed, we're going to look at the limiting speed, but we're going to also make sure that you're looking at the right one, because SKF and SKF Explorer, same name, different bearing. Explorer is the premium bearing for SKF. FAG X-Life is the premium bearing for FAG. Both SKF and FAGs, without that extra stuff on the end, run about the same. And I'll give you an example, 1250 RPM versus 2000. So you have to make sure if you're looking up apples to apples. Explorer, X-Life, the high ends, they're going to run faster than the others that are not listed that way.
So we need to make sure we put that in QM, whether or not they're X-Life or...
Anything you put in QM is good. That's the way I'll say that. Because at least if you got a picture of the bearing showing SKF Explorer, 29438, whatever it is, we know what came out of it. Any extra letters behind the bearing is very important. Any numbers typically in front of or letters in front of it generally don't mean anything. All right? Put everything, but especially the stuff from the number back. You know, a dash Y or any of these are special call-outs for different internal clearances, whether C3s or C4s, C5s. Yeah, UP, NUPs, so on. QJs are another one. There's a whole bunch of different types of stuff out there. But yes, you can calculate the speed of the roller bearing, and they are all over depending on whose brand you're buying. Okay? So just remember that as far as that goes.
Tico Westinghouse is the only manufacturer that I know that you can take a ball bearing and convert it over to a roller bearing and not have to make any type of modifications to the rotor housing or bearing caps. Now, if it was reversed, if it came in with a roller bearing and you're trying to put a ball bearing into it, that's the part where you have to watch out. With the Tico paperwork, it states that you have to make sure you machine the outer and inner bearing cap. Whatever you take off of the face, you have to take off of the register. Same with the back bearing cap, whatever you machine on the back. And Tico has the paperwork right here stating how much to take off on both faces as well. So again, ball to a roller, you don't have to do anything to it. But from a roller to a ball, you have to make sure that you're machining the outer and inner bearing caps.